Hello there. In this video, I would like to look at inverse functions. And at the start here, I'm going to briefly explain what an inverse function actually is. So here I have our usual picture that we've used in the past few videos now of two sets of numbers which are represented in this case by ovals which contain the elements. And this is set A, this is set B, and we take values of x, plug it into this function f, and then that will map to y, the set B. Now, what an inverse function is taking these values of y, which are normally the outcome of f or the range of f, and instead going backwards. So we take these and we go backwards, and this would be via the function f inverse, which we denote with a little -1 there. So you'll notice here in particular that so A is the domain of f and B is the range of f, whereas here the range of f is the domain of f inverse, if that makes sense. So remember, the domain are the numbers that we plug into the function to get an outcome. So in this case, we're actually plugging these values in, which, as I said, are the normally we think of as the domain of f, but these are then effectively the domain of f inverse, and this set A becomes the range of f inverse. So taking an example, if I take f of x equals 2x and I plug some random value, let's say I take 4, so if I evaluate f of 4, then I should get 8. So the inverse of this function, well, this function is doubling it, so the inverse function would be halving it, right? So f inverse of x would be taking 1/2 of x. And we can say that because if we plug this 8, which is in the range now, that's the end result, and plug that into here and use it as the domain, then we should get back to 4, which is back to the domain of the original function. Now, it's important to realize that in higher maths, whenever you're asked to calculate the inverse of a function, you will always be given a function which is actually invertible. But that's not to say that every function ever in existence has an inverse. So the simple way of thinking about this, or discovering whether or not a function has an inverse, is by looking at its graph. So if I take this graph, for example, and I'm going to make a basic graph of y equals x cubed. This is what y equals x cubed looks like. Now, I will tell you this has an inverse. Now, let's understand why this has an inverse. This has an inverse because if you draw horizontal lines all the way through, from the top to the bottom like this, they will only ever be intersected by the graph at one point. So that's the horizontal line test, a very simple test. If you can draw these lines and the graph only hits them at one point, then the function is invertible. If I, however, take this function here, y equals x squared, right, so this is a parabola, and I do the same test, I see that this fails the test because each line is actually intersected by 2 times, okay? Apart from, I suppose, if you took the turning point, it would only hit it once, but if any of the lines get hit by the graph twice, then it has no inverse. So let me show you the way that we actually find inverses of functions more generally. I'm going to take a simple example to start with. I'm going to take f of x equals 4x minus 2. So I would like to invert this function. Now, the way that we do this is, first of all, I'm going to replace f of x with a y. So I'm going to make this y equals 4x minus 2. And then what I'm going to do is rearrange this formula for this function for x. So in other words, we're going to change the subject of the formula to x. So again, that's kind of National 5 stuff. I'm going to add 2 to both sides, and that will equal 4x, and then divide both sides by 2, so that will be y plus, or sorry, divide both sides by 4, so that will be y plus 2 divided by 4 equals x. And I'm just going to flip these around, so that will then be x equals y plus 2 divided by 4. And then what I'm going to do is switch them back, but this is now f inverse. So this is now f inverse of x, and that y gets made into an x. So we're essentially solving this by swapping around a bunch of variables. So just to be clear, if you were to plug in any value of x, let's say you put in 2 here, then you would get 4 times 2 is 8, minus 2 is 6. Uh, let's say we take 6, so that's when x equals 2. If I then take this 6 and plug it into here, then I'll get 6 plus 2 is 8. 8 divided by 4 is 2. So I get back my original answer. So that's that's why we bother doing these inverses. Taking a second example, we have f of x equals x cubed minus 3. So again, we're going to solve this in a similar fashion by changing it to change f of x to y, and then rearranging this formula, making the subject x. So that will become y plus 3 equals x cubed. And when you move a cubed over, that becomes the cube root. So we have y plus 3, and that is the cube root of that. Then I'm just going to swap these around. So x will equal the cube root of y plus 3. And when I then make this f inverse and make y x, then I will have that the f inverse of x is the cube root of x plus 3. Here is our third and final example. We have f of x as the square root of x plus 5. So to find f inverse, we replace this with a y, so make it y equals the square root of x plus 5, and then change the subject of this formula to x. So we will have y minus 5 equals the square root of x, and moving a square root over makes it squared. So then we'll have y minus 5 all squared equals x. Then I'm just going to flip that around, so we'll have y minus 5 squared x, and this is f inverse, so now we replace the variables back, and we have f inverse of x equals x minus 5 all squared. And you could, if you want to, expand this out, but I don't think it's necessary. In fact, if anything, it would probably make it a more complicated expression for no reason. So I think taking what you want, subtracting 5 and then squaring it is probably a simpler way of writing this function.